So in the last video, we ended up with a rather lengthy note on how it is important to use all the solutions to a differential equation to get the true solution. And we left with this, that is actually a very important part, and I say almost nothing about it. That we discovered that for the second boundary condition to be true, it was necessary that k times L, that is the length of the sword, I remind you, were equal to some whole number multiplied times pi and divided by L. So what does this mean? And a better question, no, rather, the thing is, what is n? Which n is it? I mean, this is a whole number, but which one? Well, it's just as I was. I'll start over. So we have that x was equal to b times sine of k times x. All right. And now we know that k is equal to this. And this is very important because we first started assuming that the two functions were equal to some constant. I mean, to some constant c, and then we discovered that c was equal to minus k squared. But we knew nothing about any of these functions. Now we have a relationship between these constants, and a constant that we can measure the actual length of the sword. This is very important. This tells you that the differential equation is related to the length of the sword. I mean, that's interesting, right? All right. So knowing this, we can rewrite x as being the sine of n times pi times x over L. And now I can rephrase the question I was trying to do earlier, that, well, which one is it? Is it sine of pi times x over L, of 2 times pi times x over L, of 16 or 23 or whatever? Well, this is the reason I was saying in the last video that why it's important to take all the solutions, because here we have many solutions. We didn't found one x, we found many x's, we found xn. So what does this mean? This means that u is equal to x times n over xn times t, and this is equal to b times the sine of n times pi times x over L. And the time part is not free from this because the time part was t was a times e to the k squared times t over alpha. So how does this look, knowing that k is equal to n times pi over L? So this would look like this, like a minus n squared pi squared L squared times t over alpha, something like that. Yeah, I mean, you could rearrange these to make it nicer, but this is the thing. So not only we found infinitely many solutions for the spatial part, we also found that there were infinitely many solutions for the time part, which is rather interesting. And now what? Well, the thing is that there is one more condition that our solution has to satisfy, and that is that for all space, when times is equal to 0, it must be equal to x. And so when t is equal to 0, then we would get, well, these are just constants, so I'm gonna mash them up in a single constant. Is that alright for you? And I'm just call it a, because, well, yeah, I know that I say not to recycle functions, so don't follow my example. In the future use another, but I just don't want to use the or whatever. I like how this letter looks. So anyway, but here we now know that t is equal to 0, right? Because this is at the beginning. So this whole part goes to, well, it's equal to 1, because anything to the 0 is 1. So look at that. We are saying that u for all x, when t is equal to 0, it should be equal to x, and that x is equal to a trigonometric function. That cannot be right. Oh yeah, sorry if I'm using is instead of eyes. It's just I learned it in Spanish. Well, whatever. I mean, you know which function is this? It's just sine function. But anyway, so look at this. We're saying that x is equal to a trigonometric function. That cannot be. That makes no sense. But then remember that we have to use all the solutions of a differential equation, and here we are not using all of them. And so we have to add up all the solutions. I run out of document over here. All right, I'll go to the top later. So we have that u for all x equals to 0 is equals to x, and this is equal to a summation of all the solutions. Well, it's also, remember that the sums of solutions could that the multiple of a solution is also a solution. Well, let's say that it's just some constant here, that every solution has its own constant. All right. All right. So this might be true. I mean, it reminds you, at least it reminds me of how you can use Taylor series, like cosine of x is equal to 1 minus x squared over 2 plus, I don't know if I'm making this right. I don't remember. I think, no, whatever. But the point is that in the same way that Taylor series are a summation of, I think it was 4 here, of polynomials to get a function, you can also use in some other functions an infinite sum of them to make some other function. So now let's go to the top. And let's see that. Hey. All right, there's a top. All right, so let's see. We know that x has to be equal to some summation from n equals to 0 all the way up to infinity. I know that infinity might be a very big and scary number sometimes, but there's no reason to be afraid of it. Alright, so we are saying this. And probably when Fourier wrote this, it probably looked like nonsense to him. But he knew that he was too deep in and he had to continue. I mean, like he had to continue and to see if he gets some nonsense that had to be wrong, then it was wrong, like 2 equals to 3, something like that. But so far this seemed crazy, but it was plausible. So let's see. Well, how can I know how make this thing work? Well, the trick is in the constants, right? Because in the same way that, for example, let's look again at the example of a Taylor series. I'm going to. All right, I think that the Taylor series of cosine is this. I think it only uses even exponents. So what makes this series work is the constants here, the factorials of the numbers. Because here I'm just using all the polynomials, right? And the polynomial, and if I say that I'm going to write some function, that I'm going to write cosine of x as the summation from n equals to 0. Summation is right, or is summatory? I don't know. Of x times n plus some constant an, then maybe I cannot change this. I cannot change which are the polynomials. These are set, are x to the 0, x to the 1, x to the 3. But what makes the series work ultimately are the constants, the an, that is minus 2 factorial plus 1 over 4 factorial minus 1 over 6 factorial and whatever. So what can make this series work here are the constants, because I cannot change these ones. These are already set by their n. The only freedom, and the L is set and P, so the only freedom we have here is the constant. All right, so how do we find the constants? let's try to find, I don't know, like a5 for now. Let's try to find a5. So how do we find it? Let's see. So it may be useful to write the summatory or summation or whatever you said in a kind of a long way. We have a0, a0 it would be, well, let's write it just for you to see why there is no a0, times the sine of 0 plus p plus x over L. So this whole thing is 0. But we do have an a1. No, this should be a plus sign. a1 times the sine of pi times x over L plus a2 times the sine of pi times x over L plus a3. Oh, this should be, sorry. This should be sine the sine of 2 times pi times x over L, and here the sine of 3 times pi times x over L, and so on. Alright, so let's try. How could I find just one specific constant here? Well, I want all these other constants to go away. I don't need them. I need a way to eliminate all these things that I don't want and remain only with the constant I want. So I have to make something to this equation. I have to make something in both sides, and I need to end up only with one constant, the one I want. Well, let's say, what can we do? Like, I cannot subtract, because I can subtract from one side, but I would only end up with all the constant in the other side. Or I cannot divide, because by dividing I could eliminate one constant. No, but then I would end up with that constant over here. I could exponents, square roots, derivatives. No, derivatives no, but integrals. Integrals might work. Because how do I make the integral of a sine function equal to 0? That's interesting. How? And then I guess that Fourier reached this at the same point. He was probably thinking something similar to this. How do I make the integral of a sine function 0 without obviously multiplying it by 0? And then he remembered this property that you can test by yourself. That if I have the sine of a times x times the sine of b times x dx, and I think, well, what is the period? I always forget what is the period. I think it's from 0 to 2 pi dx, then this is equal, or no, this cannot be 2 times pi, whatever. No, that's actually important. You know what? I'm going to write it in a more general way, because I only know the very general way. But I think it's a good thing that you see the general from x to L, where if I have the sine, and this is gonna probably spoil the surprise, kind of, but doesn't matter. If I have two trigonometric functions, it also works with cosine actually, and they have a different frequency, and I write it this way because this way I know what the period of the function is. I know what are the limits of integrations I need to make this all be equal to 0. If you have two trigonometric functions of this form, and they are integrated in the part where they repeat each other, the period, then this is always equal to 0 if and only if n is different to m. Yeah, I mean, this is actually a longer integral to do, but I know that if you are learning about Fourier series, you can do this integral, and you can see that it always is 0 when n is different from m. Whatever they are, it can be 1 and 2, 3 million and 4, doesn't matter. As long as they are different, this integral is 0. It has to do with odd and even functions, but sadly we have no time to go into this. Actually, I think I am about to run out of time. But first I'm going to do this. So I have to. So knowing this, how do I get a 5? Well, I first would have to multiply everything by both sides of the equation by this 5 times pi times x over L. So I'm going to multiply both sides by this. Alright, so, and this is just a n of n times pi times x over L from n equals to 0 to infinity. And then I'm also going to multiply both sides by dx because I want to integrate both sides. So what is going to happen? Well, this is an integral I can make. I will make it probably in next video. But I just want you to know here that what is going to happen is that since, and from 0 to L, of course. So what is going to happen here is that since multiplication and integration are linear, this means that the integration of the sums is the same as the sum of the integrals. So this means that I would have just now a sum of integrals from 0 to L of 8 times 5. And I think it will be easier to understand if I take out the integral sign. Times 1 times, whatever, it's just a lot of symbols to remember. Times x over L plus a1 times the sine of 5 times x over L. And the same for all the other ones. It's just another integral here. I'm just going to write 2 because this is many symbols and we are already running out of time. But this is a2 times the sine of 2 times pi times x over L. And I'm forgetting the dx's, but whatever. And the important thing is that this is going to be 0, and this is going to be 0, and all of these are going to be 0. Wait a moment. And what happens when it's not 0? What happens when we reach the point when we have a5 times the sine of 5 pi x over L times a5? I mean, at some point, in this point, in the fifth one, we are going to be multiplying by the same constant and by the same function. What happens here? What is this integral equal to? How does that help us find what the value of the constant is? Well, find out in the next video about the Fourier series, where I will finally solve this and give you finally the complete formula for knowing how the temperature changes in that sort.